Hello students, now in this lecture I will deal with the topic conductance. Now this is within the chapter electrochemistry. Now what is a conductor? A species or a substance which conducts electricity is called a conductor. So, which is able to conduct electricity through it, that is referred as the conductor. Now, we will come to the difference between conductor, insulator, semiconductor when we will study solid state chemistry. At present, we will concentrate only upon a conductor and its conductance. Now, when we talk about conductor, first of all, the concept that comes into our mind is the Ohm's law. Now, it is not universally valid. This law has some limitations, actually not limitations, the criteria that must be followed while the law is to be satisfied is very typical to be maintained. That is why it is not universally applicable, but to a good approximation it is being followed by almost all systems. So, what this law states? See, this is a conductor. Now, there are 2 points. This one is A and this one is B. Now, the potential at this point A is considered to be VA and that at the point B is considered to be VB. So, the potential difference between these 2 points, which is considered as V, is given by VA minus VB. Now, as per the law, the current that is flowing through this conductor between these 2 points is proportional to the potential difference acting between these 2 points. So, if I is the current that is flowing through the cross section of this conductor, then I is proportional to the potential difference between these 2 points. But this will be followed only when temperature and other physical condition remain constant. So, when temperature and other physical condition remain constant, then only Ohm's law is going to work for any conductor. Now, this can be reversed. I proportional to V indicates V proportional to I, or V equals to I R. So, what this R is? R is the resistance. This is the proportionality constant, this R, but do not neglect the proportionality constant of any law, because in a law when you are quantitatively dealing it, it is the proportionality constant which is going to carry the signature of the system. So, the necessary information regarding the system is being incorporated in the proportionality constant. So, do not neglect it. This is the most important part. This V proportional to I will be followed by each and every conductor. Whenever we get a conductor, it will follow this relation. This is V proportional to I, that is the current flowing through a conductor between 2 points is proportional to the potential difference between those 2 points. But the rate of flow of charge through the cross section of this conductor, that is the current, will be different for different conductors, and that will allow you to compare between the power of different conductors. You can say that this is a better conductor than this one. By which term you can say that? All of them follows this relation. So, it is this proportionality constant, which is the resistance, that is going to differentiate between different conductor. So, copper is characterized by a particular R, silver is characterized by a particular R, and in this way it is this R which varies from conductor to conductor. Now, what is this resistance? Resistance is the obstruction to the flow of the charge. It is being offered by the substance. How this resistance comes? How this resistance appears? I am coming within a while. So, this is Ohm's law, and a conductor is bound to obey this law to a good approximation. So, this R is the resistance to the flow of current, and what is the conductance then? Conductance is then the ease of flow of electricity. If this is the resistance, then it is the ease of flow of electricity. So, conductance, which is symbolized as L, it is being connected to resistance by the relation L equals to 1 by R. So, conductance is reciprocal of resistance of any conductor. So, it is the obstruction and it is the ease of flow. This is the relation. Now, what is the unit? So, for this we have to know the factors upon which resistance of any conductor depends. So, this is being studied as, let us take a conductor . So, we consider that current is entering through this phase and is coming out through this phase. So, it is crossing this conductor through the two opposite phases. Now, the resistance that is offered by this conductor R is proportional to the length of the conductor. So, more the length, more will be the extent of the obstruction. If this material which is constituting this conductor is responsible for generating the resistance, then obviously if you increase the length, that will going to increase the resistance much more than the previous one. So, more the length of the conductor, more will be the resistance. And what about the cross sectional area? This one is the cross sectional area through which the electrons are crossing, or the conductor is conducting. So, R is proportional to 1 by A. So, with respect to the length of the conductor, this is length, with respect to the length of the conductor it is proportional. So, more the length of the conductor, more will be the material that is responsible for the obstructing the flow of current, and resistance will be more. But if you wish a certain amount of current to pass through any cross section, and if you increase the cross sectional area, then what will happen? With increase in that cross sectional area, it will be more easier for the current to pass through. So, more the cross sectional area, less will be the resistance that is offered to the current. So, this is the relation. Now, this is observed when cross sectional area is kept constant, and this is observed when length of the conductor is kept constant. Now, when A and L both vary, then what happens? R becomes proportional to L by A. Now, again we need a proportionality constant, so it will be R equals to rho L by A. Now, as I have said just now that do not ignore this proportionality constant. This rho is referred as the specific resistance or resistivity. So, this rho is the specific resistance or resistivity. What does this imply? Now, you see L may take any values, it may be 1 centimeter, it may be 2 centimeter, it may be 0.5 meter, L may take any values. Now, what is the value of A? It may be 1 square centimeter, it may be 0.5 square centimeter, it may be 3 square centimeter, it may take any value, it may be 1 meter square. Since this is area, we are getting it terms of squared. So, it is 1 centimeter squared, 0.5 centimeter squared. It may take any values depending upon the shape of the conductor that is being considered. Now, for a particular combination of the length and cross section, that is for this case only, that is when the length is 1 centimeter and the cross sectional area is 1 square centimeter, that is for a unit cube conductor, the amount of resistance that will be offered by that conductor is the resistivity of that species of that conductor. So, you put here when L equals to 1 and A equals to 1. So, it will be in proper unit, it will be in centimeter, it will be in centimeter square. Then R equals to rho into 1 centimeter by 1 centimeter square. So, it is rho. See, this R equals to rho. So, this resistivity is nothing but resistance. Resistivity of a conductor is also the resistance of that conductor, but having a specific length and cross section. So, the resistivity is actually the resistance offered by this conductor. You may take any value for L, you may take any value for the cross sectional area. So, that will give you different types of resistances, but when you take 1 centimeter as the length of the conductor and 1 square centimeter as the cross sectional area of the conductor, that is when you take a unit cube conductor, then the resistance that is being offered by that conductor is called the specific resistance or resistivity of that conductor. Now, we get here rho centimeter inverse. So, what will be the unit of R? Now, we know the unit of R is unit of resistance is ohm. This is the unit of resistance. So, here it will be for resistivity we will have rho equals to, we take this centimeter inverse to the left hand side and we put ohm for R. So, it will be ohm centimeter. So, this is the unit of the specific resistance or resistivity, and this is the unit of resistance. Now, we get the unit of specific resistance. So, we also write here R, rho and L. Now, what is conductance? You have just heard that conductance is the reciprocal of resistance. So, its unit will be L equals to 1 by ohm. So, it is written as ohm inverse or mho. So, we get the 3 units. Now, conductance of any conductor L is given by reciprocal of resistance of that conductor. Now, we put this expression here. So, we will get 1 by rho L by A equals to 1 by rho into A by L, or L equals to kappa into A by L. So, what this kappa is? Kappa is specific conductance or conductivity, and what we have this expression, it is 1 by rho. So, this R is the resistance and it is related as proportional to the length of the conductor, inversely proportional to the cross sectional area of the conductor, and the proportionality constant is the resistivity of the conductor. Now, when L equal to 1 and A equal to 1, we have the resistance to be resistivity. So, rho equal to R when L equal to 1 and A equal to 1. Similarly, when the length of the conductor is 1 centimeter in CGS obviously, and the cross sectional area of the conductor is 1 square centimeter, then what will happen? Then the conductance that is obtained is equal to the specific conductance. So, we put here 1 square centimeter, we put here 1 centimeter. So, it will be L equals to kappa, that is the specific conductance is the conductance. So, likewise the specific resistance is actually the resistance, we have the specific conductance to be actually the conductance, but at a particular condition, that is when the length of the conductor is 1 unit and the cross sectional area is 1 unit. Now, we have to find the unit of kappa. So, unit of the specific conductance or conductivity, what it will give us? Let us put the values. So, what is the unit of L? We have just obtained it. It is L is 1 by R. So, it is ohm inverse equals to kappa, we have to determine it, and A is 1 centimeter square and it is 1 centimeter. So, it is kappa into centimeter, or kappa equal to ohm inverse. We take this centimeter to the left hand side. So, it will be centimeter inverse. This is in CGS. Now, in SI, what would be the unit? SI unit of kappa, it is this ohm inverse or mho in CGS is replaced by Siemens in SI. So, the unit of kappa in SI will be Siemens per meter. This centimeter will be replaced by meter, it will be meter inverse, and this ohm inverse will be replaced by Siemens. So, the unit of kappa in CGS is ohm inverse centimeter inverse or mho per centimeter, and in SI it will be Siemens per meter. So, we have the definition of resistance, specific resistance or resistivity, conductance and specific conductance or conductivity of any conductor. Now, this conductance, that is L, is the property of a conductor. A conductor is a species which can conduct electricity. Now, we have two types of conductor. We are not going into that division, that is the different types of conductor are conductor, semiconductor and insulator. All we are taking about which can carry electricity efficiently, and we are at present we are categorizing the conductors into two types, that is in which mode they can carry electricity. Based on this criteria, based on this property, I am now classifying conductor. So, one is metallic and the another is electrolytic. So, the example of metallic conductor are copper, silver, aluminium, etc. And the example of electrolytes are NaCl, HCl, now here it can conduct electricity in solid state, but here for NaCl, HCl and H2SO4 either you need aqueous solution so that this NaCl ionizes in presence of water to give you ions, cations and anions, Na plus and Cl minus. So, that is responsible for carrying the electricity in case of electrolytic conductor. Or another option you have to apply heat so that it melts, and upon melting the solid state structure breaks and it will give you ions which will flow. But here what will happen? Here they develop metallic bond and a large number of copper atoms release their loosely bound valence electrons to generate a sea of electron. We know from quantum theory that microscopic particles have duality, and these electrons will will exhibit the, so this will be fuzzy, and after releasing the electrons it will be copper plus or silver plus. So, that is referred as the kernel, and that will be within these pockets. These are called kernels. So, this electron C is going to hold this kernel, and these kernels is going to hold the electron C. That is a metallic bond. So, we have a sea of electrons, a wave, a cloud having negative charge. Now, when we apply voltage here, a potential difference, say here we take a electrode having negatively charged, say here we take a negatively charged electrode, and here we take a positively charged electrode. So, this sea of electron will be repelled by this charge and will be attracted by this electrode. So, the C will shift from this negative electrode to this electrode. So, there will be flow of electron in this direction. So, current will flow in this direction as per convention. So, in a metallic conductor, current is obtained, or the conductivity is shown by a metallic conductor through the flow of free electrons. So, here electrons are responsible for, in a metallic conductor, electrons are responsible for carrying the electricity. But what happens here? If you melt it, you get cation and anion, and if you take these salts in water, you will get solvated cation and anion. Here it is in liquid form, and here it is in solvated form. In either case, you get cation and anion. So, when you apply a potential difference, a negatively charged electrode is placed and a positively charged electrode is placed, then what happens? This Cl minus show a movement towards the positively charged electrode, that is anions are getting attracted to the positively charged electrode, and what happens? These positively charged ions, these negatively charged ions are attracted to the positively charged electrode, and these positively charged ions, that is cations, are attracted to the negatively charged electrode. So, here the ions are responsible, here flow of ions actually carry the electricity. So, here free electrons carry the electricity, and here the ions carry the electricity. Now, what is the source of resistance then? See, when the electron is shifting from this negatively charged electrode away from it towards the positively charged electrode, these kernels will have vibrational motion, and through their vibrational energy they will obstruct the flow of electrons. And another thing is that this sea of electron will be attracted by these oppositely charged kernels. So, the attraction between the oppositely charged species and the vibration of the kernels is responsible for the obstruction of the flow of electron, and that is the source of resistance in case of metallic conductor. And here what happens? Here the ions are solvated here, and here it is in liquid form. Now, in case of solvated ions, the viscosity of the solution will be the source of the resistance for this conductor. Also, the interionic attraction, that is the attractive force between the oppositely charged ions, will also be responsible for the generation of resistance. So, the resistance that is being offered by a electrolytic conductor or a metallic conductor are generically different. Now, what is the effect of temperature in these two cases? If we increase temperature in case of a metallic conductor, it is going to increase the vibrational motion of the kernels. So, what will happen? If the kernels vibrate with a higher amplitude, then there will be more obstruction. So, with increase in temperature, this may be pointed out as the differences. So, the definition, that was the first point, then I have told you what is the source of resistance, that may be the second point, and this may act as the third point, that with increase in temperature, resistance of metallic conductor increases. And here what will happen? With increase in temperatures, the solvated ions or the melted ions will move faster owing to increase in the ionic mobility. So, here with increase in temperature, resistance increases, but here with increase in temperature, resistance decreases. Ionic mobility increases, speed increases, so resistance decreases. Now, our focus will be mainly on this electrolytic type of conductor. So, we will, in electrochemistry, we will deal with electrolytic conductor only, and here you see the electricity is being conducted by ions, the cations and anions, and we have learned today that we have to deal with conductance of this conductor, specific conductance of this conductor. Now, how will we measure it? If we deal with such conductors, then we have to measure the conductance, and if we know the length and area of the conductors, then we will be able to determine the specific conductance also. So, next immediate requirement is how to measure the conductance. So, that I will discuss in the next part. Stay with me. Thank you.